We now take some time to discuss additional mechanical elements present in rigid body equilibrium. These include pulleys and cables, which are not new but we will touch on again, torsional springs in addition to linear springs, and gears. We have seen a number of examples to date involving pulleys, but we'll just touch on this one issue. When should we leave the pulleys on the system and when should we remove them? If the cables coming off the pulleys are aligned with the problem coordinate system, it probably doesn't make any difference whether we leave them on or take them off. The difficulty of the problem doesn't change one way or the other. However, if the cable orientations are not aligned with the problem coordinate system, the problem can be much easier if we first remove the pulleys. Let's take a look at one example. In this example, we have a pulley mounted on an L-shaped bracket with a cable attached at B and wrapped around the pulley, coming off the pulley at an angle alpha from the horizontal. We want to determine the reactions at A and C. One option is to draw an enveloping surface around the entire structure, including the pulley. Such an enveloping surface would look like this. If we look at all the forces acting on the body that go with this free body diagram, we're cutting through the pin at A, so we will have an AX and an AY component. We have a roller at C, so we'll have just a vertical component there. And then we're only cutting through the cable at one location, and that's here, so we'll have this force. The complication that arises when we take moments about a point, probably A or C. The complication is determining an appropriate reference point for the line of action of the force coming off the pulley. What we would probably do here is slide the force backward until it comes off the pulley, and it will come off the pulley, so that will look like this. Given that the cable comes off the pulley at a tangent, we can determine the x and y coordinates at which it comes off the pulley, and as the figure here shows, relative to D, it will be r sine alpha to the right and r cosine alpha above D. The force components are F cosine alpha and F sine alpha. If our equilibrium equations included a moment about C, that equation would be minus AY times 2L minus F cosine alpha times a moment arm of L plus R cosine alpha minus F sine alpha times a moment arm of R sine alpha. Taking advantage of the trig identity that cosine squared alpha plus sine squared alpha equals 1, we can rearrange this result to give us AY is equal to minus F times the sum of R over 2L plus 1/2 cosine alpha. As an alternative, we can remove the pulley first. We know from free body diagrams of pulleys that this is equivalent to transferring the lines of action of F directly to the pulley bearing location on the frame. Since we have removed the pulley, we've also had to cut through the cable above B, so there is another force present on the free body diagram. This didn't appear in our first free body diagram because that cable segment was interior to the enveloping surface. The following movie summarizes the steps involved with this free body diagram. Here we show the enveloping surface drawn around the entire structure, cutting through the cables on either side of the pulley mounted at D. We have again our pin reactions at A, AX and AY, the roller reaction at CY, and we're cutting through the cable at two locations So we have the cable force F at B as well as the cable forces on the pulley. If we now separate the pulley at D, we have equal and opposite bearing forces on the pulley to match the cable tensions, and therefore equal and opposite forces on the pulley at D. And this is equivalent to transferring the force on the outside of the pulley directly to the bearing in both of these locations. Now, given this free body diagram for the L-shaped bracket, we would again like to write some of the moments about C. Let's make a note that we've got an F cosine alpha here, and we have a F sine alpha over on this side. The vertical components of these forces will have lines of action that go through C, so they won't contribute anything to moments about C. Over at B, we've also got an F cosine alpha here that will contribute to moments about C, but we have an F sine alpha here that won't contribute anything. So now if I write sum of the moments about C equal to 0, I have, again, minus AY times 2L, and then at B, I've got a minus F cosine alpha times L, and at D, I've got two contributions in opposite directions. I've got a plus F sine alpha times L, minus an F cosine alpha times L equals 0. And if I rearrange that expression, I get AY is equal to minus F cosine alpha plus 1/2 F sine alpha. This expression looks very different from the one we obtained by leaving the pulley on the frame. How is it that we got a different answer? It turns out we didn't get a different answer, but we have to examine the geometry of the problem to verify that this is the case. So let's go back to our original figure. Let's now examine this geometry a little bit more carefully. The hypotenuse of this triangle from B to D is L times the square root 2, because we can see that we have a right triangle and the lengths BC and CD are both equal to L. So these angles here are both 45 degrees. Because this angle is alpha, this angle is pi over 4 minus alpha, and this angle is pi over 4 plus alpha. Note then, in just using the definition of sines, we have sine of pi over 4 minus alpha is equal to the radius r over the hypotenuse L root 2. If we then just use a trig identity to expand that sine pi over 4 minus alpha, we have sine pi over 4 cosine alpha minus cosine pi over 4 sine alpha equals r over L root 2. But both sine pi over 4 and cosine pi over 4 are 1 over root 2, so this expression gives us that cosine of alpha minus sine of alpha is equal to r over L. Having established this geometric relationship, we can write sine alpha as cosine alpha minus r over L, and substitute this into the expression we obtained when we took moments about C with the free body diagram having the pulley removed from the L-shaped bracket. That gives us AY is equal to minus F cosine alpha plus 1/2 F cosine alpha minus r over L, and that gives us back the initial expression we obtained. So in spite of initial appearances, we do in fact have the same result whether we leave the pulley on the frame or take it off. In this example, we have three members pinned together to form a crude A-frame. A pulley is mounted at the end of the horizontal member BDG, and there is a cord attached at F and wrapped around the pulley in two different configurations. The problem statement requests free body diagrams with and without the pulley on the structure. We might first note in assemblies such as this, we will eventually be interested not just in the reactions at A and E, but also in the forces communicated between the different members. Those details are left at Chapter 6, but such an analysis often begins with finding the reactions at A and E, so that is our focus today. For the assembly in A, the tension T is directed downward, so there is little advantage of taking the pulley off versus leaving it on. If we draw an enveloping surface around the whole assembly, there is a single external force displaced horizontally from the bearing at G by the pulley radius. There is no difficulty in terms of formulating an expression of the moment of the external force about A or E in this approach. So in the first case, when we leave the pulley on, this cable is intact. We're cutting through at this location. We would have forces AX and AY at the pin. We have the roller force at E, and we'd have this single tension T at this location. If we draw an enveloping force where the pulley can be isolated, we end up doing something like this, and we're actually cutting through the cable twice. Now the free body diagram looks like this. We still have AX and AY at this location. We have the roller force at E, but now we've had to cut through the cable at this location, and then we've got the two tensions at the pulley, but we're transferring those to the bearings, so it looks like this and this. Note that relative to the free body diagram where we've left the pulley on, the vertical force is now transferred to the pulley bearing, and that decreases the moment that the original vertical force would exert about A or E by a clockwise amount, tension times radius. But cutting through the horizontal length of the cable also produces a pair of equal and opposite horizontal forces that constitute a couple of clockwise strength T times radius, so that the displacement of the original vertical force is now compensated by a couple of appropriate size and strength. For the second assembly, the tension T is directed at a 30-degree angle from vertical. Now there is a definite advantage to taking the pulley off the assembly instead of leaving it on. If we leave it on, we run into the same problem that we had with the previous example on the L-shaped bracket. We're cutting through the cable here, but that requires us to find the coordinates of the line of action of the force where the tension comes off the pulley, and we have to break the force into components and make careful use of the moment arms in order to impose moment equilibrium. It is easier now to take the pulley off the assembly, and then our free body diagram looks like this.